Hey guys, really excited for today's video because it's about dynamic programming. The question is that if you're given a matrix with ones and zeros, how do you find the largest possible square made of just ones? Now the problem may seem a little complicated, but just watch till the end at how simple the implementation is. So let's dive right into it. So we have this matrix and I have to find the largest possible square made by just ones.
Yep. Correct.
Okay, and the matrix can be of any dimension?
Yeah.
Okay. So in this example, then the answer would be 3, I'm assuming.
Yeah.
And also any index, which, for example, the largest possible square for this particular index, let's say this index is the top left corner, right, would be 1, which is just itself, right?
Yes.
Okay, perfect. So the first solution that comes to mind is perhaps I can iterate through this entire matrix and find for each individual index what is the largest size.
Okay.
But that would be very inefficient. So the second thing is I just mentioned that this is the top left corner of the square. Right? So in order for me to get the answer for this particular square, let's say when I'm talking about this one and this is 1, then the answer would be 4 over here, right? Because that is, or 2, sorry, but 4 ones that make 2. So if I were to go through this logic, then I would say, okay, I have 1 over here. Let me just make this 0 again. I have 1 over here. In order for me to get the solution for this particular index, when I say solution for this index, basically if this index is a top left, like for this square over here, it's a top left corner of the square, how big of a square it can make such that all of the elements in the square are ones.
Yeah.
So it would say, okay, let me look at my right, my bottom right, and my bottom one. If all of them are ones, let's say this is a 1, then I would take then the answer would be 2, right? In this case, which is basically whatever is the value of these 3 plus itself, right? So 1 plus itself. Now, if this was 0, then the value would be 1, right? Because the maximum square that it can make is just itself. So in this case, this would be 0, which is the minimum value of its neighbors, plus itself, right? So any time then, if we consider this as the top left corner of the square, any time I want to check how big of a square of ones this can make, then I will need to recurse on these 3 neighbors to see how big of squares that they can make. Suppose I have the solutions, the recursive solutions of these 3, and this one says, okay, I can make, just hypothetically, okay, not related to that matrix, I can make a square of size 3. This says I can make a square of size 4, but this still says that I can still just make a square of size 0, like I can't make a square at all. Then the answer would still be minimum these 3, which is 0, plus itself, which is 1, right? And obviously, if this is 0, then this will be 0 plus 0, which is 0, right? So let's see. Actually, if this is 0, then I wouldn't even consider it.
Okay. Yeah. That was the question I was going to ask.
Okay. Yeah.
Do you even consider going through all the neighbors if itself is 0?
Right. Right. Yeah. Because if it's 0, then it wouldn't make sense for it to make a square, right? So let's see how we can do this over here. So as mentioned, in order to compute the value for this particular index, I will need the value of this, this, and that, right? So this is a recursive solution. In order for me to compute the value of this one, I'll need the value at this, this, and this one. Actually, it looks like I'm computing the value at this particular index twice. And actually, if I want the value at this one, then I'll have to recompute the value over there. So I'm actually computing it more than twice.
Yeah.
So it's not very efficient. So this kind of triggers that perhaps this is a good candidate for dynamic programming, right? So let me erase this. let's think about this in a dynamic programming way. Obviously, I'll need some form of cache, right, for this. Let's say as I'm computing this 3 times, I don't want to do it, so I store it somewhere. And as these values then would be independent for each of these indices, I can just have a matrix of the same length and width, or the row and columns, as this one, as our cache. So let's say I have a matrix over here, which is 1, 2, and 3, and 1, 2, 3, right? And 4 actually. So one more over here, right? So if this is my cache, and I say, okay, for me to compute the value.
Do you need that extra column?
Do I need it? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Yes, I'll need it.
Oh.
Right?
Yeah.
Okay, so in order for me to compute the value for this particular index, I'll say, okay, let me recurse on this one, this one, this one. And as I'm recursing, let me just save that value in the cache. So next time when I want to compute the value of this, I'm looking at the value over here. I say, oh, I don't need the computation. I'll just return whatever I have in the cache. Okay. So I check the cache first. Yeah. And then if it's not there, then I compute it. And then save it right in the cache again. Right? So this is a solution that I'll move forward with. It's a recursive solution.
So is this the only way to go around, or can you make it iterative?
Can I make it iterative? I can make it iterative as well, actually. So I will just need to iterate through all of these squares, all these indices, and compute their own values. But obviously now, as I'm iterating through them, I will ideally want to leverage the values that I've already computed to come up with its solution. So actually then, if I'm iterating, I should consider each one of these indices not as the top left, but as the bottom right. So right now, I was saying, okay, for this particular answer, I need the answer to this, this, and this one, right?
Yeah.
Now, if I'm iterating, I'm going from 0 to whatever is the length minus 1. When I'm at this particular index, I don't really have the computation for these 3 yet, right?
Yep.
So I can say, okay, instead of me counting the index as the top left corner, let me regard it as the bottom right corner, right? So if this index is the start, is the top left of our matrix itself, then I start over there, right? And as I'm at the top left, and that is the bottom right of our square, or the maximum square it can make, then the answer is just itself. Then this will be 1. Same thing over here. So I think the leftmost column and the topmost row, the answers for those will be just itself. Then
considering they are the bottom right corner.
Considering they are the bottom right corners, yes, of the square. So I'll have 0 over here. And then when I'm here, I know the answers to these 3 neighbors. I can say, okay, in order for me to compute my value, I need the minimum value of these 3. So now the logic is the same. I'll need the minimum value of these 3 plus the value of myself. So it'll be 0 plus 1, which is 1, right? So the answer for this particular index will be 1. So let me just erase this.
So what you said, like, to calculate the value of that particular thing, you need the value of the minimum of all its neighbor plus itself.
Right.
But if it is 0, do I still do the same?
No, if it's 0, then I wouldn't go through the computation. So let me just go through an example over here, and then I'll go through the actual implementation, if that's okay.
Sure.
So I start, let's say I equals 0, and then so I is the row, and then I'm just iterating through all of the columns, right? So I equals 0, and j equals 0 right now. So I'm over here, and I say, okay, what is actually, when I equals 0 and j equals 0, then it is just itself, right? I don't need to do anything. If either one of these indices is 0, then the answer for the maximum square will just be itself. So I say, okay, this is 1, this is 0, this 1, this is 0, right? Now I'm in the second row.
Can
so
you
now
go through one of them?
Sorry?
Like why the answer will be itself?
Why the answer will be itself. So if this is the bottom right corner, then I'm looking at its neighbors. Neighbor over here, neighbor over here, neighbor over here. But these three fall outside of the matrix, right? They don't exist. So the maximum it can make is just itself.
Okay.
If I'm over here, then same thing. One of the neighbors is falling outside. So anytime one of the neighbors fall outside of the matrix, then the answer will be just itself.
Because the minimum will be 0. Then.
Because the minimum will be 0. Yeah. Anytime the neighbor is outside, then that value is 0.
Yeah. That makes sense.
Okay. So in this case now, I have all of these values, right? Then this for when I equals 1 and j equals 0, still one of its neighbors is outside. So that is itself. Now I'm at 1.
Yeah.
Right? I see, okay, I already have these three computed.
Yeah.
So I take the minimum of these three and I add 1 to it. So this will be 1 because minimum is 0, right?
Yeah.
And then I go over here, the minimum of these three, I add 1 to it. I go here, for this one, same thing, minimum of these three, I add 1 to it. Same thing over here, I add 1 to it, right?
Add 1 to it?
Sorry, this is 0, so I don't even compute it. Good catch. I wasn't even looking at the matrix. Okay, now I'm back over here. Now I equals 2 and j equals 0 again, right? So anytime j equals 0 or I equals 0, it's just itself. So I add 1 over here. Same thing. For this one, I'm computing it as it's 1, and this neighbor is 0. This will be 1, right? But for this now, it will be the minimum of these three, which is 1, and then this guy is 1 as well, so this will be 2.
Yeah.
So because I'm making this square over here of side 2.
As the bottom right corner.
Considering this as the bottom right corner. Yes.
That makes sense, yeah.
Now, as I progress forward, I'm here, right? And I look at, okay, its neighbors. And this is 1 as well. So the minimum over here is still 1. So I'll just have 1. 1 plus 1 is 2, right?
Yeah.
So this will make this square right here.
Yeah.
Over here it's 0, so I won't do anything. And for all of these bottom ones, I have 0 over there because j is equal to 0. And this will be 3, right? And for all of these, I'll just do the same thing again. So 0, 1, 1, so this will be 1. 1, 1, 2, so this will be 2. For this one, it's 2, 2, 2 actually, right? So it'll be 2, minimum is 2 plus 1, so this will be 3. And the last one is going to be 0 plus 1, so it's itself.
Yeah.
So in this case, our max value is the value right there. So actually, as we're iterating through it, we can also keep track of the max as we're going through the iterations. And at the end, we just return that value. So let me now go into the implementation.
Yeah, sure.
Let's say I have a function. And I say the name is largest square. It takes in a matrix. Right? Now the first thing I need to do is form a cache. So let me do that. I say cache, so this is pseudocode. Cache equals an array. Let's say an array of length matrix dot length, and it's an array of arrays, right? So matrix 0 dot length. All right, so actually if this was JavaScript, I would actually have a for loop and go through populating the values inside of the cache just to make sure that it's particular length. But for now, pseudocode, let's say this is basically a clone of the matrix itself. Yeah. So let's say we are now also initializing max. So max, or let's just call it result, right? Because it's going to be a result that we return at the end. result equals 0 initially. And then I go into a for loop. I equals 0, I is less than, say, matrix dot length, and I plus plus. Yeah. And then I have an inner for loop, j equals 0, j is less than matrix I dot length and j plus plus. Yeah? Okay, so now what do I do? The first thing I do is I check whether or not either I or j is 0. If they are 0, then I don't do anything. So I say if I equals to 0 or j equals to 0, then I say cache I j. So ideally I would actually clone, I would have the cache as a clone of the array itself, because as we are iterating down, we are sure that we are modifying the value, so it wouldn't really matter. So let me just simplify this a little bit, okay? I'll say this is just a clone of the array, or the clone of the matrix. So I'll say matrix dot clone.
So if it was JavaScript, you will basically be populating it with the same values.
Exactly, yeah. I'll have a for loop and I'll populate the new one with the same values. So I have matrix.clone. So in this case now, if this is the condition and it's met, then I won't do anything, right?
Okay.
Now, the second condition would be that now we have to check, okay, if this is not the case, then what do we do? So we say else if I or the value itself is not 0, then we do something, right?
Yeah.
So I say if matrix I j is greater than 0, basically it's not 0 or it's 1, then what do? We say cache I j equals, we said we add 1 to whatever it is, right? Because we know it's not 0 anyways.
Yeah.
We add 1 to the minimum value of its neighbors. So let me say min of cache I j minus 1, cache I minus 1 j, and cache I minus 1 j minus 1. Right?
Yeah.
So this looks good. Now I will close the if statement, and at the end I will modify my result.
Okay.
So I'll say if, so this is still inside of the for loop. I'll say if result, or if cache ij, let's say ij is greater than result, then result equals cache I j. Yeah?
Yeah.
And this will close our for loops. And after the for loops, actually, I'll just return the result and I'm done. So return result, and that's it.
Yeah, that's smart.
Yeah, so in order for us to kind of increase the efficiency and not compute things 3 times, we had to allocate some space, right? So we're compromising space for optimized time complexity.
Yeah.
But essentially, we'll have a n by n or n by m space complexity as well as time complexity.
Yeah, because you're just iterating.
Because I have a nested loop. Yep.
Yeah.
Thanks for watching, guys. Today's video was an excerpt from a data structures and algorithms course that I designed specifically for you to ace your coding interviews. And I've spent several months on this based on the feedback that I've gotten, and I've made so many revisions to make it just right. It's not out yet. If you want to know or just get updated when it comes out, sign up on the link below and I'll let you know. And next week, I'm going to cover the problem where you have to find the maximum area of rectangles inside of a histogram. So I'll see you next week.